to do exercise 105. Exercise 105 is it's not really a sort of problem to solve, but it's demonstrating that we have already done certain kinds of differentiation that can be, now that we've done multivariable chain rule, we can recognize some differentiation processes we've done before as arguably chain rule. So I'm doing product rule, logarithmic differentiation, and implicit differentiation. So if we say z is x times y, where x is a function of t and g is also a function of t, sorry, y is a function of t, which I'm calling g, so I'm confusing myself here, y equals g of t. Okay, so we could actually just plug those in there and have f of t times g of t, but what I'm going to do is I'm going to demonstrate that if we use the product rule, if we put the f and the g actually in there and use the product rule, we'd get the same result as if we did chain rule, multivariable chain rule on this thing here. So z is a function of x and y, and x and y are themselves functions of t. Therefore, it's legitimate to determine the derivative of z with respect to t. Chain rule says that it's dz by dx, dx by dt, plus dz by dy, dy by dt. dz by dx is y, dx by dt is f dash of t, dz by dy is x, and dy by dt is g dash of t. And then just to really make it obvious, I'm going to replace the x and y with their f and g counterparts. And that is product rule. And it would have to be. I mean, it would have to be. We couldn't have a product of functions and differentiate one way, differentiate another way, and get different results. I mean, it has to be the same result, otherwise there's something desperately wrong. But what I'm trying to demonstrate here is that some familiar results can be recognized as multivariable chain rule if we look at them a certain way. Okay, logarithmic differentiation. What if we have z equals u to the power v, where u equals x and v is also x? Okay, now you remember back in first year, if you had y equals x to the x and you wanted to differentiate it, you would have taken logs both sides. Okay, you would have done implicit differentiation on the one side and product rule on the other. There we go. That's what you do if you were doing logarithmic differentiation. Should be very familiar to you. But what we can do is we can instead use multivariable chain rule. So z is a function of u and v. U and v are functions of x. Therefore, it makes sense to determine dz by dx. And it'll be dz by du, du by d. I'm getting confused with my curlies and straight d's here. Dx plus dz dy dv, sorry, dv. V. Oh, my goodness, I'm using too many letters of the alphabet here. That's a v, and that's a v, and that's an x. Right, okay, I'm clearly rushing and making mistakes, so let me just slow down and make sure that that all makes sense. Yes, it does. Okay, so what is dz by du? Now, it's possible, I don't know how this was taught to you, but when you did your logarithmic differentiation, it's possible that your lecturer, Carpenter probably, somebody else, pointed out that if your x, so if you have x in your base, and you have a number as the power, you'd use power rule. Okay, so if x to the power n, you'd bring the n down, you'd subtract 1, and you would end up with x times, so if you use power rule on that thing, you'd end up with x times by x to the x minus 1. So it's x to the 1 times x to the x minus 1, and you can bring those powers together, and you'd end up back at x to the x. And that is, in fact, one of your terms that you end up with. If your x is the power, and you have a number in the base, like 2 to the x or something like that, then you'd use your exponential rule to differentiate. So the derivative of 2 to the x is 2 to the x ln 2. So if we use our exponential rule on that, we would get x to the x ln x. And that is, in fact, the other of our terms. So when you're doing a logarithmic differentiation, it's almost just like a cute accident that the two terms that you end up getting are one that you would get using exponential rule and the one that you would get using power rule. But if you do it through via chain rule, it's obvious why that happens. Because in the dz by du, we're treating our base as the variable and our power as the constant. And so we would use our power rule. And du by dx is just 1. Plus, dz by dv, we're treating our power as the variable and our base as the constant, and so we'd use our exponential rule. And dv by dx, once again, is 1. And then it becomes, then it's not surprising. It's not just this cute accident. It's completely obvious we're going to end up with a sum of terms where the one term is all about the base being the variable and the other term is all about the power being the variable, because that's what chain rule does. Each of the variables gets a term of its own in which it is the one being differentiated with respect to. So here we've got x to the x minus 1 plus x to the x ln x, and that is what we would get. Okay, so I think that's quite nice, yeah? From the second last of the green over here. Yes. From the second last to the last. Okay, so that's x to the power 1. So I have, my bases are the same, so I can add the powers. So x to the 1 times x to the x minus 1 is just x to the x. And then I took it out. So yes, I was kind of skipping a step there, just doing that in my head. Okay, C, implicit differentiation. Okay, we've got some function. So big F is a function of x and y, and x is just x. It's not any more complicated than that, but y is in fact a function of x. So this is implicit differentiation. This is the sort of thing where you would have typically had things like, let's have a look, what would be a typical first year problem? X, y squared plus 1 over x minus y cubed equals 3 or something. And meantime, y is actually a function of x. Can you remember doing problems like that? And then you had to use implicit differentiation. So for instance, in that first term, you would have to use product rule. And you differentiate with respect to, you differentiate the two factors one by one, and you'd end up with something like 1 times y squared plus x times 2y times dy by dx plus etc. Remember doing problems like that? That's what we're doing here, where we're seeing big F. So big F would be all of that stuff. You could maybe bring the 3 across in order to follow that equals to 0. Bring the 3 across and then say, okay, everything on the left, that's what we're calling big F. Okay? But if we treat this big F in the notation of chain rule, if we differentiate both sides with respect to x, now this looks a bit funny, dx by dx. It's not something that we usually write, but just for the sake of our chain rule notation, we have to have that there. But dx by dx is just 1. It's not a strange thing. And then, of course, the aim in problems like of the one I've written on the left there, right? The aim is to make dy by dx the subject. So let's make dy by dx the subject. I'm going to take that one term across the equal sign, and then I'm going to divide through by df by dy. Question? Yes?
How do you know that you want to make dy by dx the subject?
Well, that's usually the aim. Okay, so let's start off saying that is our aim. We want to solve for dy by dx. That's what we're wanting to do. And we're choosing to frame it in the context of chain rule. Okay, let me actually finish this one that I've written in the black here. I was only using it as a rough example, but let's actually finish it. That's actually a minus. Let's actually finish it. Minus 1 over x squared, and that would be a minus 3y squared times y dash equals 0. Sorry, I didn't leave a lot of space there. If we made dy by dx the subject of that thing, I'd be taking across all the terms that didn't have dy by dx in them, y squared minus 1 over x squared, and then I'd be dividing through with the factor that I'd get if I took dy by dx out as a common factor. So what would it be? It would be 2xy minus 3y squared, if I'm not mistaken. And that thing that's written in the black over there, that's the same as that thing that's written in the green. But it's just written in terms of the chain rule notation. But it's the same thing. The terms at the top are the terms that you get if you differentiate just with respect to x, treating y as a constant. And the terms at the bottom are the terms that you get if you differentiate with respect to y, treating x as a constant. So that's what you were doing. So you were actually doing multivariable chain rule back there in first year and you didn't even know it. Okay, all right. So those are sort of 3 illustrations of how, well, basically showing how all of calculus ties together in lots of interesting ways. And a certain process can actually be the same as a different process if you just look at it the right way. Question? It's for the sake of the chain rule notation, because the variable that's sitting, so for the sake of the audio, what's that dx by dx doing there? It's because of the chain rule, I'm wanting to differentiate with respect to x. But chain rule requires me to first differentiate with respect to the variables that are actually present in the expression, and then multiply by the derivative of those variables with respect to x. So if we scroll back to that one near the top there, I'm differentiating z with respect to u, and then multiplying by du by dx, where the x is the variable I'm really interested in. Next term, dz by dv, and then times by dv by dx, and that's because u and v are the variables that are actually explicitly in the expression. Here, I have a bit of a mixture, because one of the variables that's explicitly in the expression actually is the variable that I'm interested in. So the y is implicit, the y is in terms of x, but the x is also in a sense in terms of x. So in order for that chain rule expression to be fully fleshed out, I have to differentiate big F with respect to the variables that are actually there, which are x and y, and then in each of those terms I need to multiply by the derivative of that variable with respect to the variable I'm really interested in, which is x. And so I end up with that rather odd little situation of having a dx by dx. But that just is one. It says, how does x change when x changes? Well, it's the same. The change in x is the same as the change in x. So dx by dx is just one. Okay, it is rather odd. We don't normally end up with expressions like that. Yes?
I still don't understand how you link the chain rule to the product in question in A.
Because I chose to call the two factors, those two factors that are being multiplied, instead of calling them f of t and g of t actually explicitly in the problem, I chose to give them variable names, x and y. So I'm differentiating with respect to t, but t is not the variable that's explicitly in the expression. X and y are. Hence I have to use chain rule. Because I'm differentiating with respect to t, but the variables that are actually sitting in front of me are not t. They're x and y, where x and y are functions of t. So that's what makes it a chain rule. Okay, all right. I want to get on to 106 because 106 introduces second order chain rule, and second order chain rule can be quite tricky. So z equals x squared plus 2xy, where x is t ln s and y is 2t plus s. Okay, so the first part, a is not that much of a deal. A you just plug into the formula. Find dz by ds and dz by dt. Let's do that. dz by ds is dz by dx times dx by ds plus dz by dy times dy by ds equals. All right, and then we just differentiate. So we differentiate, Yes, I do have that right. We differentiate z with respect to the variables that are actually explicitly in the expression, which are x and y. And then we multiply by the derivative of that variable with respect to the one that we're really interested in, which is s. Okay, so dz by dx is 2x plus, come stylus, 2y times by t over s. dz by dy, 2x, dy by ds, 1. Very similar for t. Okay, once again 2x plus 2y, but this time it's ln s. And dz by dy is still 2x, and dy by dt is 2. It's not a lot of tidying up you can do there. I must admit that 2x, the second term in each of them, you don't really need the brackets, and you can turn it into 4x, but there's really not much you can do. So I'd recommend actually just leaving them like this. That's fine. It's not a problem. Yes, you've got x's and y's all mixed up with t's and s's. It's fine. If you want to replace every x with t ln s and you want to replace every y with 2t plus s, go ahead, but you don't have to. Okay, but here comes the sticky one. Derivative, the second derivative of z with respect to s. d2z ds squared. Okay, now you got to concentrate. That is the derivative with respect to s of the derivative with respect to s. Okay, all right. So the derivative with respect to s, now I'm going to write that chain rule expression in here, and it is dz by dx. Excuse me. And my children are in my office, and I've pacified them with popcorn. So, of course, as a parent, I have to take some popcorn tax. And I've got popcorn in my throat. Serves me right for stealing my children's popcorn. Shouldn't have done that. That's dx by ds. Okay, alrighty then. So, I now need to differentiate the stuff in that big bracket. That stuff in that big bracket is two terms. Each of those terms is a product. I'm going to have to do product rule. Okay? So, I want to differentiate dz by dx with respect to s. So, it's d by ds of dz by dx times by, sorry, I'm forgetting my product rule here. I can't forget product rule. Plus, okay, so product rule says that if you differentiate a product, you end up with two terms where each of the factors in the original expression gets a term to itself where it's the one being differentiated. Okay, so all of this is the first product rule. Product rule 1. And then we have plus, and then we do the second product rule. Go on, you can do it. You've done harder things than this in your life. Yes, this is why I say you need to keep your wits about you. dz by dy, and then the dy by ds just comes along for the ride, and then product rule says, okay, now it's the dz by dy that gets to just come along for the ride, and we're differentiating dy by ds. And that's product rule 2. And I've run out of page. Yes. So basically what I'm doing for each of those terms is I have a d by ds of triangle times square. Just let me demonstrate, replace them with symbols. And so product rule says I'm going to have a d by ds of triangle, and the square comes along for the ride, plus I'm going to have the triangle just coming along for the ride, d by ds of square. So, Here is a huge, big, enormous, horrible, ghastly mistake that students of calculus make all the time, and it makes calculus lecturers just lie on the ground and cry. And that is, people treat things like, well, let me do a single variable analogy. People treat this, give me my pen, and this as the same thing. They are not the same thing. The first one says the derivative of fill in the blank here with respect to x. The first one is just an operator. It says derivative of, and then you've got to put something of that after that in order for it to do anything. The second one says the derivative of y with respect to x. So this is an actual entity. It's a thing. It's a thing you can calculate, you can write it down, you can say that thing over there is the derivative of y with respect to x. But that first thing is not. That first thing is just an operator. It needs something in front of it to do anything, to be anything. It's just an operator. It's floating around in the world waiting for something to act on. So it's just d by dx. So all those d by ds's, all these d by ds's, they are operators. So what's happening over there, for instance, let me choose one I can actually reach. Over here, that doesn't say d by ds times by the thing in the brackets. It says d by ds of the thing in the brackets. Okay? So this is the derivative with respect to s of bracket times by a term. Plus, I shouldn't say a term, I should say a factor. This is some factor times by derivative with respect to s of the thing in the brackets. And if I can just belabor the point, let me do the last line. This is the derivative with respect to s of the thing in the bracket times by some factor that's not involved, plus some factor that's not involved times by derivative with respect to s of the thing in the bracket. Okay. So those are not three things. So each of those terms that are included in those black brackets there, those are not products of three things. They're products of two things. Each of those is a product of two things, where in each of these products, there's a thing that needs to get differentiated. Okay. Those are not the same things. Just to make it completely obvious in the notes. But please, 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 please don't do that. Unless you enjoy causing your lecturer pain, which maybe you do. Because it does. It causes like physical, like you got to get up and walk away from what you're reading because. Okay. It's a very, very, very. It's probably the most common error. No, I take it back. The most common error in calculus is saying derive when you mean differentiate. We should have a show of hands of how many people here have had me correct that just in the last week. It would be half of you. I can see some of you smiling, thinking, I'm one of those. Okay, so it's the second most common error. Okay, cool, so let's do that then. So let's do that. So, first black bracket says d by ds of dz by dx. What is dz by dx? It's 2x plus 2y. So now all I'm doing is I'm plugging in. All I'm doing is I still actually haven't differentiated anything. At the moment I am plugging in. So what have I done there? I've taken those lines at the top there. All the d by ds's I've just kept as d by ds's, but everything else I've replaced with what it actually is. So everywhere there's a dz by dx, I'll put dz by dx. There and there. Everywhere there's a dx by ds, etc. So all the d by ds's, all those operators are still sitting there waiting to carry out their operation, but I've plugged all the other bits in. Okay? Alright, cool. Let's differentiate. Right, very first derivative is we need to differentiate 2x with respect to s. Okay? You don't have to write what I've just written. You could jump to what it is. I'm just trying to be really explicit about what's going on here. Hooray! Finally something that isn't chain rule. The derivative of t over s with respect to s, well, that's just minus t over s squared. Whew! Harking back to our roots in single variable calculus there. Plus, what's that? That's 2 dx by ds. Plus the derivative of 1 with respect to s, that's 0. Oh, great. We've got a 0 term. What is dx by ds? It's t over s. What is dy by ds? 1. I can actually already multiply that out, can't I? But whatever. There we go, and then we're basically done. We're basically done. We can multiply that out, but we're done. We've done all the differentiation. There's no differentiation left to do. There's only tidying up algebra, tidying up some symbols. So I'm actually going to stop there. But there is some simplification that can be done. For instance, your very no, I tell a lie. I was going to say your very first term could be added to your very last term, but of course it can't because there's an extra t over s in there. But those two could be. So you could do a little bit of scrunching up and adding some terms together, but not a lot. I think it's fine like it is. Cool. Second order chain rule is quite painful. At this point, I would like to ask you to have a go with number 107, but you know what? I don't think we have time. It's already 27 minutes past. I need to do directional derivatives. So 107 I'm leaving for homework. 108 and 109 are for the next TUT. 108b is also second order. 108b, make sure that you've had your Red Bull, and you have like a choc chip cookie for sustenance, before you head into. Don't do 108b on an empty stomach or short of sleep. Okay. Okay. So that's chain rule. Please be quiet. Please be quiet. So there's two things I want to say that are comforting about chain rule. One is those formulas are actually pretty easy to memorize, and what you need are those formulas. Those formulas are your anchor. And then the second thing is you're only ever differentiating with respect to one variable at a time. So, it's just like juggling one ball. And we can all juggle one ball. Can we? I think we can. So it's kind of like we're building. What was happening here looked really complicated, but if you just take it very, very slowly, just one step at a time, there's nothing in there that really, you can't point at one particular thing and go, that thing over there, that was the complicated bit. Yes, question?
Can I find a one? Is it right for us to have x, y, z?
Yeah. It's totally okay for the variables to be jumbled, yeah. Okay, everybody take a deep breath and we're moving on. Directional derivatives. Okay, yay, directional derivatives. Let me find my notes. Hello, notes. There we go. All right, now we've spoken about directional derivatives already. I've spoken about them already. Your x and y derivatives are special cases of your directional derivative. If you're standing on the side of a mountain, on the side of some hill, some piece of landscape, and you impose some axes onto your physical landscape and say, okay, I'm going to walk in the direction of, I'm going to walk parallel to the x-axis, what is my slope? That'll be your x derivative. I'm going to walk parallel to my y-axis, what is my slope? That's your y derivative. But of course, those are only two options out of infinitely many options, because what if you went just like 1 degree away from your x-axis, or maybe 45 degrees away, or maybe you actually wanted to turn and go over off in that direction into what would be your second quadrant. So there's infinitely many directions you can walk, and the slope that you experience will depend on the direction that you chose. And those are your directional derivatives. There was a question there.
So anyway, as long as you're parallel to the x-axis, that's your
Yes, because your y is remaining constant. So if you're looking parallel to your x-axis, it's your x derivative, and the convention is you always read a slope in the direction of in the direction in which the variable increases. If x increases, what happens to y? Okay. Yeah. Oh, got a nice picture coming up, but let's do a bit of writing. Fx and Fy are the derivatives of f in the directions of increasing x and y respectively. Often, we wish to know the slope or derivative in some other direction. These are called directional derivatives. Okay, I have a little definition. And then I have a great picture. In fact, did I put the picture into the handbook? I think I did, yes. I'm very proud of that picture. It's in the box on page 35. Oh, excuse me. The directional derivative, this is probably also in the box. Definition? Yes. So I'm writing it here, but it's in fact already in your handbook, so you can save yourself some trouble if you want. The directional derivative of f at some point, x naught, y naught, in the direction of a unit vector u equals ab is, and then we have this formula equals. Now, before I even write anything on the right, let's just talk about that notation there. The big D is for derivative. Big D for derivative is not a notation that we use very often, but it is one of the standard global notations for derivative. And then that little U hat down there, that's a sort of a subscript. That's saying the direction we want to move in. And then the f, of course, is the function, and then the x naught, y naught is the point at which we're interested. So there's a lot of information packed into that small little bit of notation over there. Yes?
Is that saying that the standard is that you must always note your direction vector when you do?
Yes. You usually give your direction vector a name, which is frequently u, and it's that name that you use as your subscript. So it's not usually the vector itself, as in like open brackets. Yeah.
And then also the point, that's the point that you're trying to find the derivative.
That's where you're standing. That's where you're standing, and now you want to know what's your slope in the direction of u. Okay, and then here we have a controversial bit. H tends to 0 from above, and let me give you the formula, and then I'll talk about the controversy. Okay, there's the formula. The formula needs to be memorized. Is there any space left in your brain?
No.
Make some space. Lose your Facebook password. I mean, you don't need it anymore. I don't know. Phone numbers of people from high school. I mean, honestly, just lose that. Lose it. You need this more. You need this more. Okay. Here's the controversy. And I'm going to talk about the picture, and the picture will explain the formula. So I'm not going to explain the formula. I'll do that via a picture. But if you look in your textbook for this formula, you will find this formula, but it will not have a little plus next to that 0. It will not say h tends to 0 from above. It will just say h tends to 0. And this is the controversy, because if you look in different resources, some have one-sided limits for directional derivatives and some don't. Our textbook does not. So textbook says that it's a two-sided derivative. Now, your two partial derivatives, your x derivative and your y derivative, those are classic derivatives. They are just h tends to 0. They're not one-sided limits, they're two-sided limits. So if you truly want to think of your two partial derivatives as special cases of your directional derivatives, well, you can't if you're defining directional derivatives as a one-sided limit. What does a one-sided limit really mean? Let's say I'm standing somewhere on this hypothetical mountain and I want to walk at 45 degrees to my x-axis, so straight out into my first quadrant. What if there's this beautiful, lovely, grassy slope in front of me and I'm going to walk and everything's hunky-dory, but what if there's in fact a cliff right behind me? I'm standing right on the edge of a cliff, which I, Tracy Craig, would not do in real life at all, but this is hypothetical. So I'm standing right on the edge of a cliff. If I define my directional derivative as a two-sided limit, then the point where I'm standing is not differentiable, because it's a kink, and you cannot differentiate a kink. And so then I would say my directional derivative doesn't exist. But if I'm strictly speaking only wanting to know what's in front of my feet, so if I walk, everything's fine, then it's fit for purpose to define the directional derivative as a one-sided limit because I'm only interested in what's in front of me. So it is controversial. Not every lecturer who teaches this course chooses to define this as a one-sided limit. I tend to go with whatever the mainstream convener is doing in any one semester, and the team that's teaching mainstream this semester and has done for some years, they use the one-sided limit, so are we. Okay. However, 2015 second semester and 2014 second semester, the convener of mainstream did want to define the two, or did want to recognize the two partial derivatives as special cases of directional, and so he chose two-sided limits. So basically, if you look in a variety of textbooks, you'll see different definitions, and even if you look in a variety of resources specific to this course, you'll find different definitions. It rarely matters. Usually the two-sided limit and the one-sided limit will actually give you the same result, but sometimes it does matter. Try to remember to do one-sided limits in tests and exams, because I don't get to set the mark scheme, mainstream do, and it's possible you might actually get a mark deducted for that. Whereas for me, I don't think it's that big a deal, because I would actually prefer to have it not a one-sided limit. But I don't have perfect control over this sort of thing, and so try to remember to do it as a one-sided limit. Okay, so there's just different ways of looking at it. I can see the advantage of one-sided, I totally can. But my personal preference is for not one-sided. Okay, all right, so much about the controversy. Everybody's bored with that now. Let's look at that picture. We have 7 minutes left. Good, we can do the picture in 7 minutes. So what's going on here? All right, so let's say I'm standing on this hypothetical hill and I want to walk in this direction over here, out into my first quadrant, so not parallel to x-axis, not parallel to y-axis, but somewhere in between. What we're going to do is we're going to consider the curve that I'll be walking along. Okay, so we don't think about the whole surface. We say, okay, you're walking in that direction, right? That means you're walking along a curve. Let's look at the slope of that curve. Okay, so that's what's drawn into that picture over there. I'm standing on that curve at some point, x0, y0, z0. Okay, and I'm wanting to know what's the slope of my tangent. And the slope of that tangent will be my directional derivative. It's the slope that I'm experiencing as I walk along that curve. So the slope of this tangent is the directional derivative. Okay, so how are we going to work that out? Well, I'm wanting to walk in a particular direction. Okay, I'm wanting to walk in a particular direction. This is the direction I'm wanting to walk in. And I'm describing that direction with a unit vector. Now I'll get back to why we want it to be a unit vector. There is a very important reason, but I'll mention that when we get to it. So here is our direction that we want to walk in. So that arrow there is lying underneath the curve. In fact, it's that arrow that's defining where the curve is. down. So if I'm standing on a hillside, then I'm floating up in the air somewhere, and my XY plane is actually far below my feet, and that U arrow is down on the XY plane, and I'm wanting to walk. I'm wanting to follow that U arrow, but I'm walking like down a hill or up a hill or something. Okay. So then what we do is I'm going to take some random point that's along that U and corresponds to some point on the curve. Okay, here's what I'm doing. I've got my fixed point, x naught, y naught, z naught, and that's the point where I want to work out the slope. What I'm going to do is I'm going to take some point that's along that curve, and I'm going to work out the secant slope between those two dots, but I'm going to allow that point x, y, z to get closer and closer and closer to my point x naught, y naught, z naught, and hence my secant slope will, in the limit, become my tangent slope, okay? So this is basically harking back to, as I say, probably the very first lecture you ever had in calculus. Well, lecture, it wasn't called a lecture then. You had a point here which was probably called A, you had a point here which was probably called A plus H, and what we did was, back in high school, you looked at the slope of that, okay, and that would be f of A plus H minus f of A, and this distance here is H, and you said, okay, the slope of the secant is f of A plus H minus f of A over H. That's my vertical over my horizontal, my rise over run. And then what we did was we took the limit as H tend to 0, and hence that second dot would move closer and closer to my first dot. The secant would become more and more and more the tangent, until in the limit the slope of the secant is the slope of the tangent. That's exactly what we're doing here, except instead of our curve being a nice flat curve in the xy plane, it's a space curve. But other than that, it's exactly what we're doing. Yes?
When you do it from both sides, does that mean that you would face the other direction? And then x would come, x, y, z would come?
No. See what I'm doing here? I've drawn in a second arrow that's parallel to the U, and I'm calling it HU. So that as H tends to 0, so does HU tend to 0. And basically what we are, I suppose, because if H was negative, we would be considering basically flipping U in the other direction, yeah.
Minus z would be smaller than x naught, y naught, and z.
Well, that'd be, on the other side of our fixed point, and we're not considering that. We're only considering x, y, z on the one side of our fixed point rather than on the other side. Okay, so what we're doing is we're saying, okay, here's U. U is fixed. U is a unit vector. It's 1 unit long, and it can't change. But if we take U and we multiply it by H, and then we allow H to change, well then that shorter arrow there, it can change. So what we're going to do is we're going to allow H to tend to 0, so that short arrow gets shorter and shorter and shorter. The point XYZ gets closer and closer and closer to our fixed point, and we start to approach our tangent slope. So what I'm going to do is I'm going to just draw what's happening in the XY plane. Here's my X naught and here's my Y naught. Here's my U. Here's my HU. I should have had that popcorn. It was 2 kernels, 1 from each child. Got to be even. Got to steal evenly from your children. You can't steal asymmetrically. Important parenting tip there. Okay, where was I? Drawing. Okay, so I wanted to talk now about why we want this to be, am I ready to talk about that? About why we want U to be a unit vector. No, I'm not ready yet to talk about why it's a unit vector. But now, basically what we're doing is we're saying Z, the Z, if you look at this, X, so U is AB, right? So HU is HA, HB. So this X here is X naught plus HA, and this Y here is Y naught plus HB. Sorry, I can see I've reached the end of the period, but I think basically that's it, really. After that, we just want to plug into a typical slope formula, and our typical slope formula, we want the limit as h tends to 0 of delta z over h, which is the limit as h tends to 0 of z minus z naught over h, which is the limit as h tends to 0 of those. Oh, that's jolly music. Y naught. Okay. All I'm doing here basically is writing down the formula now. I've derived the formula. Well, derive is a strong word. I've justified the formula. And then we impose one-sidedness on this limit. Okay. All right, I'll stop there. There's a little bit more I want to say, but I'll do that on Monday.